This is the pre-lab lecture for experiment 7, where today we're going to be preparing buffer solutions. You're actually going to be creating 2 buffer solutions in the lab today of specific pHs and then measuring experimentally how good a job you did. And then we're going to have a couple of other buffers of varying concentrations, and we're going to be testing how well they actually can maintain their pH, what their buffering capacity is, another way to say it. Now, in preparing buffers, if you want to make an effective buffer with a specific pH, the most important thing is the weak acid you choose to make that buffer. Because to make an effective buffer with a specific pH, you have to choose an acid with a pKa as close as possible to the required pH. Let's say you're making a buffer with acetic acid. If that's the weak acid, then the weak conjugate base would be the acetate ion. So a buffer with acetic acid and the acetate ion. If acetic acid has a Ka of 1.8 times 10 to the minus 5th, we can take the negative log of that number and get its pKa, which turns out to be 4.74. So the acetic acid acetate ion buffer would be a good acid-base combination to make a buffer around a pH of 4.74. So the acetic acid and acetate ion can actually be used to make any buffer that has a pH anywhere from 3.74, which is 1 pH unit lower than 4.74, all the way up to 5.74, which is 1 pH unit above. But it's only good for that range. If you needed to make a buffer with a pH of lower than 3.74, you need to pick a different acid conjugate base combination. A buffer with a pH higher than 5.74, you need a different acid-base combination in order to make that. So in part A of the experiment today, they want you to prepare a buffer that has a pH of 9.50. So we're going to need to pick an acid that has a pKa close to 9.50. Now this problem specifically tells you how to make it. They want 50.0 milliliters of some weak acid solution mixed with some correct volume of a strong base solution. So in this technique, this is one of the 3 ways we've learned to make a buffer. We've learned you can make a buffer by mixing solutions of a weak acid and a solution of its weak conjugate base. In this case, we're going to be mixing a weak acid, and it's going to have to be with a lesser amount of strong base. The 3rd way you can make a buffer is by mixing a weak base solution with a lesser amount of strong acid. But if we can identify that we're going to be mixing only these 2 chemicals, the weak acid and the strong base, we know this will make a buffer as long as the strong base has a lesser amount than the weak acid. And we're going to be able to calculate how much of the strong base by using the amended Hasselhoff equation. Hasselhoff equation, pH equals pKa plus log of the amount of the weak base over the amount of the weak acid. But if you're adding a strong acid or base to the solution, or it's a component of the solution, we've got to amend this equation because the strong base will react away the weak acid, so we subtract the amount of strong base in the denominator. And it actually turns the weak acid into the weak base, so we have to add the amount of strong base to the numerator. So this is the amended Hasselhoff equation. We're going to use this for our calculation. Let's see if we can determine what weak acid we have to use for this. They've given us in the experiment a list of chemicals that we can use in the experiment today, but what we have to do is figure out which one are we going to use as the acid. Also given in the experiment was a list of acids with their Kas and pKas. And if we go through each of the acids, H3PO4 has a pKa of 2.12, H2PO4 minus, pKa of 7.21, HPO42 minus, pKa of 12.68, acetic acid, we saw earlier, 4.74. And then the ammonium ion's an acid. It has a pKa of 9.25. Well, we have to pick the one that's closest to 9.50. So that means the ammonium ion has to be the acid in our buffer. Of all the chemicals that we have available to use in the experiment today, the only one that contains ammonium ions is the ammonium chloride. So we're going to use that in order to prepare the buffer. So let's go to the calculations we need to do. In the Hasselhoff equation, we know what the pH is. It's going to be 9.50. We know what the pKa of the ammonium ion is. It's 9.25. We've got to calculate all the values in our log term, and one of those values is the moles of the weak acid in the buffer. So how do you get moles of a component? You go molarity times volume. Now, what's the molarity of the weak acid here? Well, we know it's coming from the ammonium chloride, which was 0.40 molar. And because ammonium chloride has 1 ammonium ion in its formula, You just have to multiply the molarity of the ammonium chloride by 1. And so therefore 0.40 molar ammonium chloride will have in its solution 0.40 molar ammonium ions. That's the concentration of the ammonium ions. The volume of the weak acid solution we're going to use is 50.0 milliliters. We're going to multiply those together. 0.40 moles of ammonium per liter multiplied by, converted to liters, 0.0500 liters. So that's going to allow us to determine how many moles of ammonium are going to actually be in the solution. So that's the moles of the ammonium, which is the weak acid. What's the moles of the weak base in the solution? Let's see, if the ammonium ion is the weak acid, take a hydrogen off, the weak conjugate base is going to be ammonia. Are we adding any weak base to this solution? We're adding 50 milliliters of a weak acid with a strong base. We're not. So therefore, the moles of the ammonia, which is the weak conjugate base, is going to be 0. That sometimes freaks students out where one of the variables, they don't have it given in the problem. What could it possibly be? Well, you're going to see quite often in these buffer calculations that one of the components is going to be missing, and you have to recognize its number of moles is going to be 0. So there aren't going to be any moles of the weak base in there. So in the calculation for the moles of the strong base, and remember we're trying to figure out the values for everything that's in the log term here. We already know the pH is 9.50, the pKa is 9.25. We've now calculated the moles of the weak acid that goes in the denominator is 0.020, and the moles of the weak base at the top has to be 0. We've got to calculate the moles of the strong base that we're going to be adding to this solution. So all the values I'm going to plug in, the pH 9.50, pKa 9.25, the weak base, which is the ammonia, there's none of it because nobody's putting any ammonia in this solution. The weak acid, we just calculated, is 0.020. So now we only have one variable, that is the amount of strong base. So the only way you can figure out how much is going to be in there is by solving the Hasselhoff equation for that variable. So here we go. Let's plug all the numbers in. Let's see if we can solve that. So in this expression here, the first thing I would do is I would subtract 9.25 from both sides of the equation. If we do that, the left side will become 0.25, and that's going to equal our log term, which on the top was 0 plus moles of strong base. So I just simplified that to moles of strong base. And in the denominator, it's 0.020 moles minus the moles of strong base. If I raise each side of the equation to 10 as a base, or take the antilog of each side of the equation, the antilog of the left side turns out to be 1.7 with a 7/8 as 2 guard digits. And the antilog of the right side is just going to be what you have in the parentheses. It's just going to be the moles of the strong base over 0.020 moles minus moles of the strong base. Let me move that up to the top, and let's continue. I'm going to now multiply both sides of the equation by my denominator, which is 0.020 moles minus n. And if I do that, they'll cancel out on the right side, and the 0.020 moles minus n will now appear on the left side. I'll now do the distributive property, 1.778 multiplied by 0.020, and 1.778 multiplied by negative n, and that's going to equal n moles of strong base. To collect all the n terms on the right side, I already have one n on the right side. I have negative 1.778 n on the left side. I'm going to add 1.778 n to both sides, and I'm going to wind up getting 2.778 n on the right and my 0.03557 on the left. Divide both sides by 2.778, and we'll get the number of moles of strong base that had to have been placed into this solution to make the pH 9.50. So we now know we need 0.012 with a guard digit 8 moles of strong base. Now, what is that strong base we're actually putting in here? If we go back and look at the list of chemicals that we could have used in this experiment, there's one strong base in here. That's the sodium hydroxide. So that means that our moles are going to come from this 1.000 molar sodium hydroxide. And because we know its molarity and we know how many moles there need to be, we can figure out what the volume has to be to provide that number of moles. And here's how we do that. If you know there are 0.0128 moles of NaOH that must be in that solution, we're going to multiply this by its molarity, but I'm going to invert it. I'm going to put the 1.000 moles on the bottom and the per liter on the top, so just the inverse of the molarity. Moles will cancel out. That's going to tell you how many liters of the sodium hydroxide solution you're going to need. That comes out to two significant figures, 0.013 liters or 13 milliliters. So you will see in the lab today, they're going to mix 13 milliliters of the sodium hydroxide solution with 50 milliliters of the ammonium chloride solution, and they'll actually measure the pH of the buffer. We'll see how close it comes to 9.50. You're going to do a similar calculation now to predict how to make the buffer in part B. And then in part C, you're going to be given different buffers of different concentrations, and you're going to be determining their buffering capacity by adding strong acid and strong base to them.